The next keynote speech today is from Professor Hongming Xu. Professor Hongming Xu is Chair of Energy and Automotive Engineering and head of the Vehicle and Engine Research Center at the University of Birmingham, and distinguished visiting professor at Tsinghua University. He was one of the pioneers in the early 2000s in using artificial intelligence for design and control of powertrain. And the software developed by his group has been procured by industry and also used in hybrid vehicle design. The topic of Professor Xu is development and outlook of artificial intelligence system for future electrified powertrains. Let's welcome Professor Hongming Xu. I see Professor Xu is online. It's very late in UK. Please.
Thank you, Chairman. Hi, everyone. Good morning. My name is Hongming Xu. Today, I'm delighted to have this opportunity to share my talk. Many thanks to the organizing committee. Now let me share the slides. The title is Artificial Intelligence Systems for Optimal Control of Future Electrified Powertrains. With a little background and challenges, let's set the scene. This is today's scenario of our road transport system. For over 100 years, we're talking about ICE engines. Now we're talking about electrified vehicles, where at the heart of the vehicle is the propulsion system. And the control of operation of propulsion system now is being moving to control based on artificial intelligence, which would gradually replacing the main experience-based decision making. And the powertrain systems for electrification is moving from the combustion engine to the combination of the battery, motor, and so on. The peak power of the dedicated hybrid engine reaches 40 plus 43, 40, and plus as indicated by BYD recently launched the new hybrid engine. Then more development now is on not only on the engine itself, but also with the powertrain system for the connection, automation, sharing, and electrification. As predicted by the International Energy Agency, within the next 20 years or so, we will see half of the engine will be working using hybrid. And by year 2050, we will see almost all vehicles will be electrified, including plug-in hybrid, of course, battery powered and fuel cells powered electrified vehicles. And the work remains to be done for the combustion engine in the next 15 years also is to continue to improve efficiency. After that, the new fuels will be very important to decide how long we can use combustion engines, and for sure to meet the low carbon and or decarbonization target. Then, in parallel with the work on the engine and battery, now the powertrain control on the second row of the diagram predicted and on the roadmap by the ICAVP shows that artificial intelligence-based full control will be the future for our powertrain system operation. The software development for the control will become such a big job that within the next 10 years' time, we're expecting there's 100,000 times increase of the complexity, and even to 10 to the power of 8 by 2040, where the computing power continues to increase and the cost continue to decrease, and the time left for the product development need to be halved or even more than halved, and the increase of the efficiency, work efficiency, will continue to increase. We all know that for not only the engine, but the battery or the motor, for sure, we need to work in a higher efficiency region. This will pretty much depend on the control system to make sure the powertrains will be working for the wide range of speed and the load conditions. They are always going to work within the high efficiency region. The new legislation for vehicle testing for hybrid, including for hybrid, will be based on a real driving emissions testing, RDE, or the real world driving enhanced driving conditions. It's all need to be considered at the early stage of the product development. That needs to be considered in the control for all the power unit, including the engine, not only using the traditional way of rule-based control using big data bank, but also it's going to use adaptive control for constrained optimization using forward and backwards closed loop or open loop, model-based or non-model-based online prediction for the future. So the artificial intelligence will start to become more and more important, not only as used for the early stage for modeling or the optimization, but in end is for the predictive control, eventually for autonomous decision making. In the very early stage of the work is the classic issues of artificial control using model-based predictive control. And that is where the artificial intelligence started use in the combustion engine development. And following that methodology, the work we developed is the real-time engine models, and using the model-based real-time prediction of the engine performance, we have seen the control system can complete the spark timing or without spark timing for HCCI engine operation control. The current version of the development work is to represented by two dimensions of diagram and presented by industry. At Ford, Dr. Wang has been showing that the work for offline static control need to be replaced and moving gradually to online optimization, and the gain or the fixed gain rule-based control gradually moving to online adaptive and constrained optimization. If we consider both of the dimensions, then we are moving to the right direction in the end. There was we have the online dynamic optimization control for our powertrain systems. So that is our target, and the work is on now for 4 levels, and starting from the unit level, including engine, motor, battery, etc. Then on the interaction between power systems components and systems is the powertrain level control. Then on the vehicle level, we need to involve drivers' behaviors and also the road conditions. On top of that is a fleet level and proton control for the whole traffic optimization of the traffic and energy flow. So this will need to be carried out in collaboration with all our research partners and at the different levels of Tier 1 to Tier 3, Tier 4 suppliers, and also the OEM. On the engine basis, the AI's application has been shown starting from the average control. Now, aftermarket, coherent or incorporated control systems are starting to show advantages. And for the combustion system development work on the imaging processing using artificial intelligence. Perhaps the most attractive advantages being demonstrated is the artificial intelligence-based engine calibration. And the control of the vehicle level is starting from the powertrain systems and moving for perception to decision making. In the end is for learning to continuously improve the engine, powertrain, and the vehicle control, not only in the laboratory, but also in the virtual laboratory conditions in the end for the real driving conditions. The 3 areas of part of the artificial intelligence work has been used so far for the powertrain control, starting again from the traditional calibration, classical question of average control, now moving to model control, driver's model, etc. This is using, for example, fuzzy logic has been one important area, and multiple objective organization using evolutionary algorithm has been typically used for intelligent engine calibration and component sizing work we'll demonstrate later on, and on the top level online intelligent control. However, the most attractive, exciting work is on the model-free online prediction of the for the complex system control. The work at Birmingham as a demonstration is based for the engine testing facilities developed over the last 20 years. And we have 15 different engine test beds, including single-cylinder diesel engine, gasoline engine, optical engine, transient operation, etc. So all that development work now need to be reconsidered to use for electrified powertrains. Part of the testing bed can be converged to testing of the motors, but part of the engine test bed or the transient test bed has been now being used as a part of the closed loop development work by connection through the driving simulator by the open ECU of the controller, connect to the vehicle controller, connect to the vehicle itself. So the lab car system has been used as part of the loop for representing the vehicle on the road by developing advanced vehicle models. Now we can control the engine power train units and testing the real motor, testing the real battery, or testing the real engine. But the vehicle can be incorporated onto the different platforms of the vehicle models. And the road conditions is coming from the data where connect the outside world to the combustion or the powertrain or the power unit testing laboratories, and the big data from the cloud web services provided by Amazon has been proven very useful. So that is how we arrange our work into two different categories. Major sections. One is using the control units and developing a software using AI-based control algorithms, models, and then interact with the control of the laboratory's operation, including both the hardware on this one side and the software on the other side, shoulder by shoulder. And with the two units, with hardware is at the heart of the core of the powertrain is the engine or the motor or the battery. And the vehicle itself is a virtual environment testing condition provided from the big data service. That's the structure of the current powertrain control development framework. The layers of the framework, starting from the data collected from the ADAS development work team, using the V2X and data collected to the sensors and integrate into the vehicle, and then pass through the strategies planning and the series planning, and all this need to be now integrated onto the powertrain testing facilities we showed you earlier, including hardware and the software. The algorithm used for multiple optimization is typically using evolutionary algorithms shown by the swarm and particles, and it's vivid the birds or swarms from nature. Now, this advanced algorithms has been developed for many years, as we showed this literature survey, and the development was to make the algorithms faster and faster, and make it able not only for offline optimization, but also for real world online optimization. So this job is not only being done by computer science scientists, but also by engineers. Here is an example of how we, as an engineer, mechanical engineers, can make a contribution to make the improvement on the algorithms and to make it more suitable for our purposes. The traditional capsule or the APSO algorithms is using the two vectors. So the modification to these two vectors now allowed us to make a chaotic selection of the optimization points movement include to not only fixed directions, but according to the step-by-step optimization to be elastically, flexibly to choose the directions of the searching and of the optima. So that is being proved as very successful. For most advanced or the recent development on machine learning or reinforced learning is to for the future's model-free predictive management on the vehicle system. And this publications we list here is an example of the work we have done, where the Q-learning methods has been used, where the parameters of the engine or the powertrain unit's operation is written into the equations represented by the coefficient or the parameters, in the end being formulated into a rewarding factor according to the performance of the vehicle or the powertrain unit. Then this Q-learning method has been upgraded as a so-called multiple state information fused methods is to, by step repeating the Q-learning and gradually to achieve decision-making parameter selection through the multi-layers of steps of the Q-learning operation. And the details of this method have been summarized in publication. So we are not going to in the details, but we just want to show how much we can do as mechanical engineers can work on a practical application of the artificial intelligence algorithms. So the algorithms has been written into the control system, where this is the expertise of the vehicle engineers to develop advanced vehicle or the engines models, powertrain units models, and combined with the control algorithm-based control system the strategies. And this strategy now it can be used for the control using the prototype controller. Then the demonstration of the advantage is to show that the comparison between the original main power calibrated engine performance, now the fuel consumption, for example, has been reduced by AI-based calibration, better than the long hours of main-based calibration process. So this is an advantage to show the control of the engine can be much faster, much more responsive now to show that close follow-up of the requirement, demand of the throttle for the air-fuel ratio precisely control following the need. And the settling time has been reduced by 75%. So the efficiency has been increased, and that control algorithms has been written into the offline real-time development model, first of all, to calibrate some models in the engine model here. In this one, it's a diesel engine. Then also on the control models, also use the advanced algorithm so that it's operating on the engine testament bed with using an open ECU. The comparison of this control algorithms for the calibration has been compared in this table, shoulder by shoulder, which shows the advantages of the AI-based model. Free control algorithm is to achieve global optimization, whereas DOE-based or data-driven models can only achieve a local optimization. So this comparison has been done with industry. So the software we are talking about here now has been procured by one of the biggest model company in the world to use it for future engine for the engine's development. So this same AI-based algorithm toolbox has been used for development of the first, the world first hybrid vehicle on the airport to move vehicle airplanes, and that shows the intelligent sizing by using the multiple objectives capsules can reduce the energy losses while at the same time reduce the powertrain unit volumes. And the cross functions has been improved over the time of evolution by iterations. Then the performance of the vehicle is following optimal control strategies quite well, and that is the hardware we use for the development work of this hybrid. Now is in production. And this diagram shows the advantage of the learning process without using intensive testing in laboratory. The efficiency of the hybrid can be starting from a lower level, but gradually it's going to improve and reach the maximum in the end for a certain period of time. You can see for all the different testing conditions that the using different algorithms, of course, we can achieve different level of improvement of efficiency that implies or indicate how much work we can do with the advanced self-learning algorithms. So for the future, we have to bear in mind the hardware computing power still increase rapidly, and the ICT's technology, we're talking about 5G today and 6G tomorrow, will still have a lot of space to development, further development, and of course here the intelligence, including artificial intelligence, work of human beings' experience, also all increase. The combination of the three will make the future product development achieve a different way as we see from today. Typically summarized as a cyber-physical system combination and merging the control for the classic control and also for the future machine learning control. The control of the hardware and software and development work for vehicles can be seen that it will increase and rapidly, and we will see in the loop of the calibration in the end will be sitting on the digital twin technology or the hinge of the technology. So what the digital twin is, we already know, but the use of the control strategies is not only on the vehicle level itself. Here is to show the work of the control system we develop is going to work on 4 layers: the classic controller, and online learning, and the global optimization, cloud-based, and there's big data for storage of the data. So this system is already being seen in the development of our mobile phone in our hands. So similarly, our vehicle and also the power system will use the control system as we see the software are running our mobile phones. To summarize, finally, that electrified power system will still see a lot of work on combustion engines in the next 10 years for continuous development to have high efficiency, but of course, low carbon fuels will be important. But we're already seeing that the artificial intelligence-based control system will be the major task, not only for the engine, but also for the battery, motor, fuel cells. All these electrified vehicles will have more platforms for us to work on using artificial intelligence-based control, benefited from the big data advancement of the hardware and the AI-based control. And the digital twin is the future enabler for our more and more advanced power system. all this development work at Birmingham is documented in those publications, which can be found from my website. And that's the end of my talk. I wish to thank you for your attention, and I welcome you
all. Thank you, Professor Xu.